Assalamu alaikum. I'm Dr. Muhammad Zahid with yet another lecture in renal physiology, and today we will discuss the reabsorption in the proximal convoluted tubule of the kidney. This whole discussion will focus on three main questions. What are the substances reabsorbed in the proximal convoluted tubule, and what are the mechanisms involved? What is the role of the proximal convoluted tubule in acid-base regulation? And what if the proximal convoluted tubule stops its function altogether? So by end of this lecture, you will be able to answer these questions. So let's not waste time and get started. Here we have a schematic diagram to discuss the reabsorption in the proximal convoluted tubule. That is the first part of the nephron. Here on my left hand side, we have the tubular lumen, which contains the glomerular filtrate. The tubular lumen is lined by tubular epithelial cells, and we have taken one such cell for reference here. And here on my right hand side, we have the renal interstitium. The part of the tubular epithelial cells facing the tubular lumen is what we call apical membrane or luminal membrane, and the side that faces the interstitium is called the basolateral membrane. Reabsorption in general involves multiple steps. In the first step, any substance to be reabsorbed is taken up by the tubular epithelial cells. In the second step, that substance is dumped into the renal interstitium, and still later it is flushed away by the blood flowing in the peritubular capillaries. Here in the proximal convoluted tubule, the reabsorption of everything else, be it glucose, be it amino acids, be it lactate, or be it potassium and chloride, the reabsorption of everything else is linked to sodium reabsorption. Sodium reabsorption is the cornerstone here in this case. And the reabsorption of sodium itself is dependent on the activity of the sodium-potassium ATPase pump in the basolateral membrane. This pump continuously pumps sodium out of the cell and potassium into the cell. As a result, we have high potassium, a buildup of high potassium within the cells, and the intracellular concentration of sodium is very low. So as a result of the activity of the sodium-potassium ATPase pump, we get three types of gradients. The first one is the concentration gradient. Since the intracellular stores of sodium are very low as a result of the activity of the sodium-potassium ATPase pump, and we have a higher concentration of sodium in the glomerular filtrate because it is an ultrafiltrate of plasma, so the concentration of sodium and every other electrolyte here is in proportion to its plasma concentration. In the case of sodium, it approaches about 140 millimoles per liter. So after a concentration gradient has been achieved, sodium can now move into the cell and from a region of higher concentration to a region of lower concentration. We also call downhill transport. The downhill transport from the tubular lumen into the proximal convolute into the tubular epithelial cell yields energy that is utilized to transport glucose, amino acids, and lactate as well into the cell. And we have specific transporters for this purpose: the sodium glucose cotransporter, the sodium amino acids cotransporter, and the sodium lactate cotransporter. The second important gradient as a result of sodium reabsorption is the osmotic gradient. After sodium has been reabsorbed into this tubular cell and then into the dumped into the interstitium, the relative osmolarity within the tubular lumen drops and it becomes higher on the interstitial side. So water follows sodium through the paracellular pathway, that is through the gaps in between adjacent tubular epithelial cells. So as a result of that osmotic gradient, water too moves out of the tubular lumen into the interstitium. And then on its way, it takes potassium and chloride as well, a phenomena we call solvent drag. So this is how sodium transport causes the osmotic reabsorption of water along with potassium and chloride. As a result of sodium reabsorption, we also get one more gradient, that is the electrical gradient. Sodium being positively charged, after it has been reabsorbed or taken up by the tubular epithelial cells, the inside of the tubular lumen becomes slightly more negative as compared to the inside of the tubular epithelial cell because of the loss of positively charged ions. So that paves the way for reabsorption of chloride to maintain electroneutrality. So this is how the activity of the sodium-potassium ATPase pump helps establish three important gradients to help reabsorb sodium along with glucose, amino acids, lactate, and then water, potassium, and in addition to its reabsorptive role, the proximal convoluted tubule also helps in the regulation of acid-base balance. As a result of glomerular filtration, like all other electrolytes and other substances, bicarbonate too is filtered into the tubular lumen. A failure to reabsorb this filtered bicarbonate and its excretion in urine may cause the risk of development of metabolic acidosis. Here in the proximal convoluted tubule, we have an enzyme expressed called carbonic anhydrase, which catalyzes the formation of carbonic acid from carbon dioxide and water. The carbonic acid dissociates into bicarbonate ions and hydrogen ions. The hydrogen ions thus formed are transported into the tubular lumen through the sodium-hydrogen countertransporter, where the hydrogen ions combine with the filtered bicarbonate to make water and carbon dioxide. The bicarbonate ions thus formed in the tubular epithelial cell of the proximal convoluted tubule are disposed into the interstitium in one of the two ways. It is either pumped into the interstitium through the sodium bicarbonate cotransporter, or alternatively, the chloride bicarbonate countertransporter may pump bicarbonate ions out of the cell into the interstitium in exchange of chloride ions that are pumped in. Well, having discussed the reabsorption in the proximal convoluted tubule, it sounds quite logical at this point to ask ourselves, what if the proximal convoluted tubule doesn't reabsorb what it absorbs? Since the proximal convoluted tubule is the largest reabsorptive area of the nephron, it accounts for reabsorption of over 65% of the filtered load of sodium, potassium, chloride, and water. At the same time, it reabsorbs about 100% of the filtered load of glucose and amino acids and over 90% of the filtered load of lactate and bicarbonate. If the proximal convoluted tubule fails to reabsorb these substances due to one reason or another, these substances will remain in the tubular lumen and will be delivered to the later segments of the nephron, where the reabsorptive capacity progressively declines. In that case, the later segments of the nephron will not be able to handle such a huge load, and most of these substances will be excreted in urine without any regulatory intervention by the body. So we can say the body can't afford the failure of proximal convoluted tubule, and for the same reason we don't have any drug in clinical practice at the moment that can completely block the reabsorption in proximal convoluted tubule. However, we have few drugs here used for some other indications which selectively block the function of the proximal convoluted tubular cells. For example, as we discussed earlier, the reabsorption of the filtered bicarbonate within the proximal convoluted tubule is dependent on the enzyme carbonic anhydrase within the tubular cells of the proximal convoluted tubule, which catalyzes the formation of carbonic acid from carbon dioxide and water. The carbonic acid thus formed then dissociates into bicarbonate ions and hydrogen ions. The bicarbonate ions thus formed are transported first into the tubular interstitium and then reabsorbed in the bloodstream, while the hydrogen ions thus formed are transported into the tubular lumen through the sodium-hydrogen countertransporter in the apical membrane. In the tubular lumen, the hydrogen ions combine with the filtered bicarbonate to make water and carbon dioxide. So this is how the filtered bicarbonate is reabsorbed in the proximal convoluted tubule. We have a drug by the name of acetazolamide used in closed-angle glaucoma and benign intracranial hypertension, where it reduces the synthesis of aqueous humor and the cerebrospinal fluid respectively. While it is used for some other indication, this drug is an inhibitor of the carbonic anhydrase, and as a result, the proximal convoluted tubule, owing to the inhibition of carbonic anhydrase, will not be able to reabsorb the filtered bicarbonate, and that bicarbonate will move on to the later segments of the nephron. The distal segments have a limited capacity to reabsorb bicarbonate, and so most of it will be excreted in urine, and the body will land in a situation we call proximal renal tubular acidosis type 2, all because of selective inhibition of the proximal tubular cells. Similarly, we have a drug by the name of Empagliflozin and dapagliflozin, which selectively block the sodium glucose cotransporter in the apical membrane of the proximal convoluted tubule. Inhibition of this cotransporter inhibits the reabsorption of glucose in the proximal convoluted tubule. It stays in the tubular lumen and delivered to the later segments of the nephron. Most of it remains unabsorbed and excreted in urine. So this is how the body gets rid of the filtered glucose, of the excess filtered glucose, and the plasma glucose concentration stays within normal limits. But selective inhibition of the sodium glucose cotransporter results in loss of or excretion of huge amounts of glucose.